Now we are going to try chapter 4, problem number 33. And in this one, we have a volleyball player doing a jump spike. They slam the ball from overhead and toward the opposite floor. Controlling the angle of the spike is difficult. Suppose the ball is spiked from a height of 2.3 meters with an initial speed of 20 meters per second at a downward angle of 18 degrees. How much farther on the opposite floor would have landed if the downward angle were instead 8 degrees? So one of the issues that students seem to have with this one is understanding what they mean by the downward angle of 18 degrees, because some students put this angle right here. However, we can tell from the contextual clues in the problem, if we have a downward angle of 18 degrees and then it's going to go further with a downward angle of 8 degrees, then that would imply that our angle right here is actually the 18 degrees. For 8, that would be a shallower angle right here, and it would go further as they're suggesting. And so that's the first hurdle to get over. So there's our 18 degrees as our downward angle. And so then from there, what we need to do is we need to figure out how far we're going to go with this situation, and then how far we're going to go with 8 degrees instead, and then ultimately what's the difference between those two things. So I'm going to start by writing out all the things that I know and what I want to know. And so in the x direction for this, well, first of all, we remember that this is 20 meters per second at this 18-degree angle, and this is a velocity, and we're able to figure out our x and y velocity here. So my velocity initial in the x direction is going to be 20 times cosine of 18 degrees, because that'll be this right here. And so that will equal 19.02 meters per second. We remember that our acceleration in the x direction, since this is projectile motion, is 0. And I'm going to say that my initial x position is 0. And we are trying to solve right now for our final x position. And we really wish that we also had time, because if we had time as well as velocity, then we could figure out our position, but we don't have this. Fortunately, though, we do have some information in the y direction, and so hopefully we can use that to find our time. And remember that the time in the y is going to be the same as the time in the x, and so once we get it over here, we'll use it in our x information. So here's our y information. We know that initial velocity in the y direction is going downward, so I'll call it negative 20 sine 18. So that's this right here. And this equals a negative 6.18 meters per second. Our acceleration in the y is negative 9.8 meters per second squared. My initial y is going to be right here. I'll call that 0. And if that's the case, and my downward direction is negative, then my final y is going to be negative 2.3 meters. Again, we don't know our time, but we wish we did. And we also don't know our final y velocity, which we will figure out in just a minute, and I'll show you why. So my first goal right here is to figure out the time that it takes. And so there's a couple different ways of going about this. First, we could try using this kinematic equation, y equals y naught plus v naught yt plus 1/2 ay t squared. And this actually will work fine. Let me show you how it works. So our y right here, negative 2.3 equals 0 plus negative 6.18 t plus 1/2 negative 9.8 t squared. And so if we want to work this out, that's fine. It's slightly mathematically difficult because I have a t squared and I have a t. If you have a graphing calculator, you can figure this out pretty, hopefully, easily. And so you would find out that your t would equal negative 1.5, and it would equal 0.3. And so it doesn't make sense in this context to have a negative time, so then our answer would be 0.3. But you might be in a situation where you don't have a graphing calculator, or you forgot the quadratic equation, or you don't feel like dealing with that. And so you could find out your time in a different way. What you could also do is you could use the equation v equals v naught plus at, all of these in the y direction, But as we notice, we don't have our final y velocity, and so we'll need to do an additional step to get there. And so if we want to do that, we could use v squared equals v naught squared plus 2a delta y. Of course, all of these being our kinematic equations that we're able to use if we have a constant acceleration, which we do. So in this case, I have my v squared equals my v naught, so negative 6.18 squared plus 2 times 9.8 times negative 2.3. And so if I work this out, I find out that this v squared equals 83.27, which means that my vy final equals 9.12. And now I can plug back into this equation. So we know that our vy final is in the negative direction. So I have negative 9.12 equals our initial y, negative 6.18 plus negative 9.8 times time. And if we work this out, we find out that our time is 0.3 seconds, which is what we found up here, but we just didn't have to use any sort of quadratics to get there. So now we need to figure out our distance in the x direction. And so we'll go about that by using our kinematic equation, x equals x naught plus v naught xt plus 1/2 ax t squared. And so x equals 0 plus our initial x velocity, 19.02, times our time that we just found, 0.3, plus 0, since our acceleration in the x is 0. And we find that our distance here is 5.72 meters. So now what we figured out is how far it goes in the x direction if we're spiking it at 18 degrees. And so if I want to know how much further it goes with 8 degrees, then I'll have to do the problem essentially all over again, but with a different angle. And so I will sketch that quickly. So here is now our 8-degree angle. And we're going to go through the exact same process. And so this time I'm going to use our quicker process to get our time. And so we'll have, I'll draw a line here, y equals y naught plus v naught yt plus 1/2 ayt squared. So we have negative 2.3 equals 0 plus, oh, and of course here we need to have our information in the y direction with our new information. So v naught y equals negative 20 sine 8, which equals negative 2.7835. So I'll go over here, plug it in. Negative 2.7835 times time plus 1/2 negative 9.8 times time. And we find out from this that the only viable time that we can use, because it's our positive time, would be 0.45763 seconds. So now we have the time with this other angle. And we could have gone about it in this way too, if we didn't want to use a quadratic, but it's your choice. There's a lot of different ways to go about doing kinematic problems in this way. But now that we have our time, let's jot down what we know in our x direction. So v naught x equals 20 cosine 8, which equals 19.805 meters per second. And so to find out our x distance, we have x equals x naught plus v naught xt plus 1/2 ax t squared. So x equals 0 plus our x velocity, 19.805, times this new time, 0.45763, plus 0, since we have no acceleration in the x direction. And we find out that our distance here is 9.0633 meters, which, fun fact, that would have gone out of the volleyball court because volleyball courts only, so hopefully somebody else hit it so you didn't go out. But that's not the point. The point is how much further would it have landed with this angle? So we'll have to take this number and subtract this number. So 9.0633 minus 5.72 equals 3.35 meters. So our ball will go 3.35 meters further with this smaller downward angle. We are done.